The Sun's magnetic field has reversed, marking the peak of solar cycle 25 as we enter the solar maximum. This phase of heightened solar activity brings significant changes, with the Sun releasing storms more violent than ever before. Concerns are growing on Earth about the potential catastrophic effects of these solar storms, especially on satellites and other vital technological systems. Space entrepreneurs like Elon Musk are already preparing for worst-case scenarios, while NASA issues near-daily warnings about new dangers posed by the Sun's activity. Over the past few months, the intensity and frequency of solar storms have reached unprecedented levels. Researchers predict that the peak of this solar cycle will occur in 2025, with even more violent solar events expected. Some satellites, already operating near their limits, could face significant challenges in the coming year. In the summer of 2024, Elon Musk shared images of stress curves on Starlink satellites, revealing that the newly deployed satellite network had narrowly withstood the Sun's bombardment. However, the future remains uncertain, as scientists warn of the possibility of a horror storm, capable of plunging Earth into unimaginable chaos. Solar maximums are characterized by heightened activity, including increased sunspots, solar flares, and coronal mass ejections (CMEs). These phenomena result from the Sun's internal dynamics, particularly the reversal of its magnetic field, which occurs roughly every 11 years. In May 2024, an exceptionally large sunspot region, named Active Region 3664, appeared on the Sun. This sunspot grew to 17 times the size of Earth in just a few days, highlighting the intense upheavals within the Sun's layers. Sunspots appear darker because they are cooler than their surroundings, a result of powerful magnetic currents creating cavities in the Sun's surface. Solar flares and CMEs often accompany sunspots, releasing vast amounts of charged particles into space. When these particles reach Earth, they interact with our planet's magnetic field, concentrating at the poles and creating spectacular auroras. Normally, these lights are confined to polar regions, but recent geomagnetic storms have caused auroras to appear in unexpected locations, including the Mediterranean, Australia, and Hawaii. In fact, one of the strongest geomagnetic storms in the last 500 years recently illuminated skies far from the poles, a testament to the current solar activity's intensity. NASA has expressed concerns about the impact of these solar storms on space-based technology. A recent solar flare classified as X9.5, the strongest in 7 years, prompted fears for the safety of the International Space Station, ISS, and numerous satellites. Solar storms can disrupt technical systems, potentially leading to communication outages and data losses. If critical supply systems on the ISS fail, astronauts' lives could be at risk. Furthermore, disruptions to satellites could cripple Earth's communication networks, creating widespread chaos. The current solar cycle is a reminder of humanity's vulnerability to the Sun's activity. Historically, solar storms have had profound effects. The Carrington event of 1859, the most powerful solar storm ever recorded, disrupted telegraph systems, caused fires, and generated panic worldwide. Sparks flew from telegraph wires, and the skies burned with vibrant colors for days. At that time, technology was far less advanced, and the storm's effects were limited to telegraphs. However, a similar event today could cripple modern civilization, given our dependence on electricity and satellite-based systems. The Sun's cycles have been studied since the late 18th century, but our understanding of their long-term patterns remains incomplete. While researchers have identified an approximate 11-year cycle of activity, they cannot yet predict with certainty the occurrence of extreme events like the Carrington event. Scientists are working diligently to monitor and forecast solar activity, but the Sun's complex behavior poses significant challenges. One of the Sun's most dramatic effects is on Earth's magnetic field. This protective shield, generated by the movement of molten iron in the Earth's core, deflects charged particles from the Sun. Without it, our atmosphere would erode over time, leaving the planet uninhabitable. Mars, for example, lacks a magnetic field and has lost much of its atmosphere. Similarly, exoplanets like Proxima b, despite being located in their star's habitable zone, may be rendered lifeless by intense stellar flares. The magnetic field also gives rise to the auroras, one of Earth's most beautiful natural phenomena. These shimmering lights are a visible reminder of our planet's defenses against solar storms. However, recent geomagnetic storms have stretched these defenses to their limits. Experts warn that if the magnetic field were ever overloaded or collapsed entirely, the consequences would be dire. In such a scenario, Earth's atmosphere could degrade, and life as we know it would become impossible. NASA and other space agencies are exploring ways to mitigate the risks posed by solar storms. For now, the focus is on improving forecasting models and strengthening the resilience of satellites and electrical grids. However, the reality is that we cannot prevent solar flares or CMEs. We can only prepare for their effects. Ensuring the reliability of critical infrastructure is essential to minimizing the impact of future solar storms. The Sun's current activity has sparked debates about its potential influence on Earth's climate. While increased solar radiation theoretically could affect global temperatures, no significant warming has been observed to date. The particles from solar storms do not carry enough energy to alter the atmosphere's temperature significantly. Thus, while solar activity poses risks to technology and communication systems, its impact on climate remains minimal. Despite the challenges posed by solar storms, researchers are optimistic about humanity's ability to adapt. Advances in technology and a better understanding of the Sun's behavior will help us navigate future solar cycles. However, the unpredictability of these events underscores the importance of continued research and preparedness. The lessons of the Carrington event and other historical solar storms serve as reminders of the Sun's power and our dependence on Earth's magnetic field for protection. As we look to the future, the Sun's activity will undoubtedly continue to shape our understanding of the cosmos and our place within it. While solar maximums bring challenges, they also offer opportunities for scientific discovery and innovation. By studying the Sun, we gain insights into the fundamental processes that govern our solar system and the universe beyond. In the face of these challenges, humanity's resilience and ingenuity will be our greatest assets. One key area of focus is the phenomenon of coronal mass ejections, CMEs. These massive expulsions of plasma and magnetic fields from the Sun's corona are among the most powerful events in the solar system. A large CME can release 1 billion tons of material traveling at speeds exceeding 3 million miles per hour. When these energetic bursts are directed at Earth, they can create geomagnetic storms capable of disrupting power grids and causing widespread blackouts. Efforts are underway to better understand the mechanisms behind CMEs, enabling earlier detection and more precise impact forecasting. The current solar maximum has already demonstrated the Sun's capability to produce events of unprecedented scale. In July 2024, a CME narrowly missed Earth but delivered a glancing blow to several satellites in geostationary orbit. Operators scrambled to mitigate damage, providing a stark reminder of the fragility of space-based infrastructure. Starlink and similar satellite constellations, which aim to provide global internet coverage, are particularly vulnerable to heightened solar activity. Protecting these systems from long-term damage requires innovations in shielding materials and satellite design. Meanwhile, NASA and other organizations are investing heavily in space weather monitoring missions. The Parker Solar Probe and the European Space Agency's Solar Orbiter are key assets in this effort. These spacecraft provide unprecedented close-up views of the Sun, gathering valuable data on solar winds, magnetic fields, and particle emissions. By studying the Sun from within its atmosphere, scientists aim to unlock mysteries about how solar storms originate and evolve. The effects of solar activity extend beyond technology, impacting human life in space. Astronauts on the International Space Station, ISS, face heightened risks from radiation during solar maximums. The Earth's magnetic field offers some protection, but astronauts venturing further, such as to the Moon or Mars, will be exposed to much higher levels of radiation. Space agencies are exploring solutions, including advanced shielding and improved mission planning to minimize exposure during peak solar activity. Solar storms also hold implications for our growing reliance on renewable energy. While solar panels are designed to harness the Sun's energy, they are not immune to its extremes. Intense solar flares can induce voltage spikes in solar arrays, potentially damaging equipment. Ensuring the stability of renewable energy systems in the face of solar disruptions is an emerging challenge as the world transitions to greener technologies. Looking ahead, researchers are exploring the broader implications of solar cycles on Earth's ecosystem. While the direct influence of solar activity on global climate remains minimal, scientists are investigating potential connections to regional weather patterns. For example, changes in the sun's ultraviolet radiation can impact the ozone layer and atmospheric circulation, subtly influencing weather systems. The ongoing solar maximum also provides opportunities for public engagement and education. The appearance of vibrant auroras in unexpected locations has captured the public's imagination, fostering interest in space science. Citizen science initiatives, such as monitoring auroras or tracking sunspot activity, allow enthusiasts to contribute to the understanding of solar phenomena. Thanks for watching Space Lab. Don't forget to like, subscribe, and share your thoughts below. Until next time, keep exploring the cosmos.